Hello and welcome to the OpenNebula as the infrastructure provider at the Sylva project screencast. During this screencast, we are going to showcase how OpenNebula is integrated with the Sylva software stack, where it serves as the underlying infrastructure layer. We will demonstrate how this integration automates the deployment of Sylva-compliant Kubernetes clusters and the validation of cloud-native network functions on top of those clusters. We will start with a brief introduction to the Sylva project, then present the key OpenNebula enablers that make this integration possible. After that, we will walk through the deployment workflow before diving into a detailed demonstration where we deploy both management and workload clusters. What is Sylva? Sylva provides a telco-grade cloud-native stack based on the open source technologies designed specifically for telecom and edge services. The project centers on a Kubernetes-centric foundation, aligning the entire software stack with the principles of the Cloud-Native Computing Foundation. This enables a GitOps-style approach of the operations for the full lifecycle management and automation of both the clusters and the CNF running on them. The Sylva stack is designed to be modular and flexible, supporting many deployment scenarios across different cloud providers and bare metal servers. In the figure on the screen, you can see an example of the Sylva deployment. At a central site, the bare metal servers are provisioned with a virtualization layer managed by an infrastructure as a service provider. In our screencast, this infrastructure as a service provider will be the OpenNebula instance. On top of this, we can deploy management and workload clusters that can host any cloud native workload, particularly CNFs for telco applications. These central clusters can then manage various edge sites, extending the container platform to the far edge. To support the deployment of Kubernetes clusters, OpenNebula has implemented two standardized cloud-native interfaces. The first is the Kubernetes Cluster API and our implementation that is codenamed CAPONE, that stands for Cluster API Provider for OpenNebula. This provider allows the full lifecycle management of Kubernetes clusters on top of OpenNebula. Its source code is openly available and it's used directly by the Sylva framework to create both management and workload clusters. The second one is the Kubernetes Cloud Provider Interface. OpenNebula's implementation of the CPI enables the runtime management of Kubernetes resources like load balancers and persistent storage. CAP1 relies heavily on the functionality provided by the CPI. Together, these two open source components enable the seamless integration of OpenNebula into the Sylva software stack. During the Sylva workflow, the framework uses the Cluster API and Cloud Provider Interface implementations we've just discussed to manage resources on the OpenNebula cloud. The process begins when a user configures and runs Sylva tools. In the background, the Sylva code interacts with our Cluster API implementation, CAP1. The first major step is bootstrapping the management cluster. Here, the Sylva tools communicate with the OpenNebula instance to create the virtual machines that will host the Kubernetes management cluster. Once the management cluster is up and running, it takes over the responsibility of managing the workload clusters. It deploys the new virtual resources on OpenNebula, installs Kubernetes, and configures any enabled Sylva units on that workload cluster. After this step, the infrastructure is ready for the deployment of the CNFs. Before we jump into the demo, let's quickly describe what we are going to do. First, we'll inspect the OpenNebula instance that we have prepared for this demo. Then, we will clone the official Sylva core repository and, following the official guide, configure the values file for the OpenNebula's cluster API provider. Next, we will launch the Kubernetes cluster deployments, starting with the management cluster and then the workload cluster. We'll monitor these deployments from the perspective of OpenNebula. Finally, we'll access the workload cluster and deploy a simple container and verify that everything works as expected. This is the OpenNebula instance we are going to use. As you can see, there is one pre-deployed and pre-configured virtual machine that will serve as our control node for running the Sylva commands. In addition to this virtual machine, we will rely on the pre-existing virtual network named service. All the virtual machines deployed for our Kubernetes cluster will be connected to this network. We can inspect the same information from the OpenNebula command line. Here we can see our control virtual machine and the details of our service network. Now, let's go to the official Sylva documentation to see the prerequisites. The first common step is to set up a virtual machine with a specified set of tools. Our control node virtual machine has already been configured with these tools. These prerequisites include Docker, Python libraries, YAML, JQ, YQ, and others. As you can see, they are already installed on our control VM. Next step is to clone the Sylva core repository. We'll access our control virtual machine and clone the repository there. Following the Sylva guide, our next step is to customize the configuration values. Inside the freshly cloned repository, we can already see the necessary integration files for OpenNebula. In this values file, we will configure the deployment for both our management and workload clusters. As you can see, the upstream repository provides a template that we will need to fill in with our environment-specific values. This includes the public network's name as known by the OpenNebula, the master and the worker virtual machine templates, and the image names. We also configure the number of worker nodes and control plane replicas here. This is where we configure the virtual IP for the Kubernetes cluster's API server. The file should also specify which Sylva units we want to enable. I have already prepared these value files for our OpenNebula environment. We can see that this file has been updated with our specific values. The virtual network name is service just as we saw earlier, and we have specified our master and worker templates. We also assigned the cluster virtual IP, which must be an allocated IP from the same subnet as our service network. In the values file, we can also specify which Sylva units we want to deploy. For this demo, we'll have a very minimal cluster setup, but we must enable CAPONE, which is OpenNebula's cluster API implementation. We're also going to use Ranger to manage the Kubernetes cluster within the Sylva stack. Next, we will verify that our OpenNebula installation has its RPC service running and accessible. This is how the Sylva software stack sends management commands to it. First, we confirm that the IP address is assigned to an interface on the OpenNebula host. Secondly, we check that the OpenNebula RPC server is listening on its default port. Now we are ready to move our prepared value files into the Sylva core repository on our control VM. I'll upload the file for both the workload and management cluster from my local machine. The next step is to bootstrap the management cluster on top of the OpenNebula. For this, we will use the bootstrap script provided in the Sylva core repository. This script is going to deploy the virtual machines on the OpenNebula. The script is now communicating with OpenNebula via the cluster API. It is creating the virtual machines for the control plane and worker nodes for our management cluster. You can see the virtual machines appearing in the OpenNebula interface, going through the provisioning and booting states. Once the VMs are running, the script will proceed with installing and configuring Kubernetes on them. Now let's access the control plane of the management cluster to verify it's a working Kubernetes deployment. As you can see, the names of the worker nodes and the control plane node matches what we saw in OpenNebula. The Sylva stack has created many namespaces for the enabled Sylva units. If we are going to check the pods in all namespaces, we can see that they are all in a healthy and running state. As was mentioned, we are using Rancher. By port forwarding the Rancher service, we can access its web interface. We need to retrieve the initial admin password from the deployment, which is a generated secret. As you can see in the Rancher dashboard, we are able to see our management cluster along with the number of deployed pods and resource utilization. So we have reached this point. The management cluster is up and running. The next step is for the management cluster to deploy our workload cluster. For this, we will use another set of scripts from Sylva software stack. These scripts will synchronize the desired state and create the workload cluster. Note that the Sylva stack is moving towards a full GitOps workflow, where these commands would be triggered automatically by changes in the Git repository. We will continue to monitor the deployment of a new virtual machines from OpenNebula's perspective. So the script has finished. And as you can see from OpenNebula's perspective, new virtual machines have been provisioned for the workload cluster. We can see the nodes having the same names as they do in OpenNebula. We can list the namespaces and pods, which show the deployed Sylva units for this cluster. Again, all pods are in a healthy state. If we take another look at the Rancher's deployment, we can see the new workload cluster is also recognized and managed by Rancher, showing its status and resource usage. Now, as a final step, let's deploy a simple container in the workload cluster to confirm it's fully operational. First, let's create a new namespace. Then, we'll create a pod definition for a simple application that just prints a hello world message to the logs. Now, let's create this pod in our new namespace. We can see its status, the execution was successful. And if we look at the container logs, we can see our message printed correctly. This concludes our demonstration and the screencast. We have successfully shown how OpenNebula can serve as a robust infrastructure provider for the Sylva project, automating the deployment of a telco-grade Kubernetes cluster from start to finish. The screencast was produced in the scope of One Edge 5G project. Thank you for your attention and see you in the next screencast.